Hi, and welcome to our third and final lesson for the MOSAMAC Lesson 2 Extension project. Today we're going to be talking about the geologic time scale and how scientists developed this really cool graphic outlining the history of life on Earth. If you recall from the first lesson this week on Monday, or part 1 of Lesson 2E, we talked about scientists thinking that the Earth could be up to 4.5 billion years old. That's an insane amount of time. We talked about how scientists can look in different rock layers, and understanding the law of superposition can help us put a relative age on rocks. We learned that index fossils can also help us determine a relative age of rocks as well. For instance, if we know a fossil of a creature lived in a certain time period, we could know that the rock we were studying was also from that time period, just because those index fossils were present. So the rock layers that we study give us a really interesting picture of Earth's history. And so by studying these rock layers, scientists have come up with what we call the geologic time scale. And there are lots and lots of different ways to depict the geologic time scale. This one is pretty compact and fairly easy to read. And I want to go over a few key vocabulary terms so that you understand when looking at a geologic time scale what it is they're talking about. So the word eon is the largest division of time. And we basically have only 2 eons. Let me see if I can make this bigger here. So there are 2 eons. We have Precambrian time and Phanerozoic. And Precambrian is pretty sketchy. We don't really have a lot of information about Precambrian time because it was so long ago. And quite honestly, life forms, if any, were very, very simple and just simply didn't fossilize well. We really truly believe the first life forms on Earth were bacteria. And although we do have some very rare forms of bacterial fossilization, it's pretty rare. So the next division of time is the era. An era is smaller than an eon. And we still consider Precambrian down here as, I guess, considered an eon. So there are 3 eras that occurred after Precambrian time. We have the Paleozoic, the Mesozoic, and the Cenozoic. So I always remember the eras always end in zoic. And meso means middle. That one's in the middle. Now these mark major divisions of time, usually marked by mass extinctions. So the end of the Paleozoic, at the end of the Permian period, was marked by a huge extinction, like 95+% of life on Earth went extinct. And we're not exactly sure why, but we see in the rock layers after the Permian that the life forms in the fossilized record are very, very different. So this would be a mass extinction. This would be a mass extinction. We're currently still in the Cenozoic era. Now, periods are smaller than eras, and they are marked by different dominant life forms. So, the Devonian, which is a very interesting time period in the Paleozoic, is sometimes called the age of fish because fish were evolving many different life forms, and there were varieties of fish swimming in the oceans. And during the Paleozoic, most of the Earth's surface was covered with oceans, warm, shallow seas. And so there was a lot of really cool aquatic life. Now, you'll notice here we have named epochs. That's this word right here, epoch. And beyond that, there's not really any specific name, just early, middle, late. It's really, really hard to divide up these time periods into anything more specific because the farther back you go, the harder it is to divide up time into smaller chunks, and there's not a really great fossil record. But since the Cenozoic, geologically speaking, has been more recent, we have a lot more information about the geologic time scale for our current era. So we have 2 periods in the Cenozoic. We have the Tertiary and Quaternary, and sometimes the Tertiary is broken up into two smaller pieces, which I actually don't really know what they consider those sub-periods. These down here are sometimes called the Carboniferous, but they're divided into Pennsylvania and Mississippi in here. But we have a lot of information about the Tertiary and Quaternary time periods. So we call these epochs. And these are marked by different events and different fossils that we find in the fossil record. And sixth graders, you should know this. At the very beginning of the sixth grade science year, we talked about biodiversity. And one of the things that's currently being discussed is whether or not we are in a new epoch in the Quaternary. And they're considering calling this newest time period or epoch the Anthropocene. And you can see they all end in ocene. The Anthropocene is the age of humans. So we did talk about that at the very beginning of the year. Now, on this particular geologic time scale, you can see how many millions of years ago each of these divisions of time occurred. So I'm going to zoom back out and I'm going to show you real quickly a different geologic time scale that you may see. I really like this one. This one just breaks it up a little bit differently. This is Precambrian, so the oldest, then Paleozoic, Mesozoic, and Cenozoic. So this is from the Geological Society of America, and you can see that they have some different breakdowns, which is not super important for us, but they go a little bit further. Within epochs, you have age, and then millions of years ago. So this one just kind of fits on one nice, easy to print worksheet. All right, so there are some great geologic timescale videos. Normally, we would read The Journey Back in Time from our textbook. We've actually watched this a little bit in science class this year. This is my all-time favorite, The History of the Earth. So honestly, if you've got some time on your hands, these might be some videos to check out. The History of the Earth is an hour and a half long. I found a really cool series in PBS. Called Eons, and there's this is the first episode. There's tons of episodes. If you click right here, it'll put it in a mix. So before I give you today's echo assignment, I have a little bit of extra time. I didn't get to this last year, but I do want to share it with you a little bit today. So we've been talking about relative age of rocks, a span of millions of years, older than, younger than. There is a way that scientists can take rock samples to the lab and determine a more precise age. And that's done by radiometric dating. And I had a really cool experience a few years back at a teacher PD in Washington, D.C., actually with Mr. Henderson, and we learned a little bit about radiometric dating in the lab. So basically, radiometric dating takes a rock sample with some sort of a radioactive element and traces how much of that element has decayed. And without getting into the details about how you tell what half-lives are, it's basically just a set period of time we know it takes for one element to change into another element. And so we can take rocks back to the lab, and by running these rocks through a machine, we can tell how much of the original element is there and how much has changed or decayed into a new element. And it can tell us how old a rock is. It's pretty cool. We have quite a variety of elements that can be traced, and a few of these have half-lives in millions or billions of years. And that's how we got the approximate age of the Earth, by sampling rocks that we believe are really, really old. For instance, this particular element, uranium-238, decays into lead-206 every 4.5 billion years or so. So, it's depending on human machines, and there's always the proximal error, but it is pretty neat. So Mr. Henderson and I got a chance to go to some labs in the Smithsonian where they actually look at crystals and rocks under high-powered microscopes. This is actually a microscope. It's pretty cool, right? And they look at the elements present in rocks, and in some cases, they even take samples of meteorites and determine the age and composition of them. So we got to take a look at that microscope. And then this machine is a spectrometer, which can take a rock sample and it basically can show the scientist what elements are present in the rock samples. And they get these really small rock samples by firing lasers at these rock samples to study them. So here's Mr. Henderson and I. We are literally, with the click of a mouse, shooting lasers at rock samples to determine or to help determine the age of these rocks. Another really cool thing I got to see while I was at the Smithsonian in DC was a very, very old layer of rock. And the theory that dinosaurs were killed by a meteor is actually a very well supported theory. If you went back to your geologic time scale, the end of the Mesozoic, which is the age of the dinosaurs, is right here at the end of the Cretaceous. So it's about 65 million years ago. And after the Cretaceous, you see very, very few of the big reptiles. They're gone. And all across the world, any rock samples that were studied showed this irregular pattern in the rock cycle. We now call it the KT boundary. And this is a thin layer of iridium dust. And iridium is an element that's pretty much only found in asteroids, meteors that hit the Earth. And it's very widespread across the globe. So at about a rock layer where we would approximate 65 million years ago, we see this irregularity in layer of iridium. So this is the actual rock layer showing the layer of iridium, believed to be evidence for the mass extinction of dinosaurs at the end of the Mesozoic. So it's pretty cool to be able to see that. I actually got to hold what we believe are some of the oldest rocks that humans have ever had their hands on. This was a special lab that had rocks from space. We got to look at some rock samples from the Mars lunar rover, or I'm sorry, the Mars rover and also the lunar rover. So samples from the moon and from Mars that tells us the approximate age of rocks on those celestial bodies. So it's pretty cool. We got to touch them, but we had to wear gloves. So what are you going to do today? We have done all of the lessons from 2E. The last thing you need to do today is actually a fun little puzzle. You're going to solve the crime using your knowledge of superposition. This is called the whodunit superposition riddle. And if you want, you can take some time to go back through the other lessons and the videos. Think of some good questions you might want to ask me at the Zoom meeting on Thursday. We'll see you on Thursday at 11:30.